All right, now let's look at identity function. This is leading into inverse functions. So the definition of an identity function is that for any set A, the identity function on A is a function from A onto A, denoted by I, or capital or lowercase, okay, or more specifically I of A on that set, such that I of A equals A for all A in A, lots of A's. So basically this is, you can kind of think of the identity function as f of x equals x, right? Right, so example 6, let's see, so basically for all functions onto a set A, you can show that if you compose the function with the identity function, or compose the identity function with the function, then you get the function itself. So that's why it's called identity. Like 1 is a multiplicative identity, because if you multiply a number by 1, you just get itself. The identity function is identity in the sense that if you compose it with any function, then you get the function back to itself. Okay. So in this example, let's say the set A is 1, 2, 3. Let's find the identity function I that goes from A to A. Okay? So basically, identity function will take a number and just turn it into itself. So I1 is 1, I2 is 2, and I3 is 3. Or if you want to give it a formula, we say IA equals A. If you want to look at the identity functions over the real numbers, so can extend the set from just 3 integers to the real numbers, then you can't list them, so you just write it as a formula. So the identity function for x being a real number is that returns x. So this is the function I of x equals x, which if you graph it, right, this is basically the line y equals x. Okay, so each coordinate point, each input that you put in there, it gives the same value for the y. Okay. So now let's define an inverse of a function. So if I have a function going from set A to B, if there exists a function g going from B to A, sort of switching the domain and the codomain, such that g composed with f equals the identity of A, and f composed to g equals the identity on set B, then g is called the inverse of f and is denoted by f to the negative 1. Okay? The inverse of a function is unique. So basically, if I compose g with f, and I get back to the inputs, and if I compose f to g and I get back to the inputs in B, then f reverses g, g reverses f. And they're called inverses of each other. Now, the functions that have inverses are bijections. Okay? So, for a function to have an inverse, or if I have a function from A to B, the inverse exists if and only if f is a bijection. F is 1 to 1 and onto. And the reason for that is because in order to invert the function, like switch the domain and the codomain, right, the inverse needs to be a function itself. So if it's 1 to 1, that means it fulfills like property 1 of functions, that each element in the domain only goes to one y value in the codomain. And the onto, that kind of fulfills the first property of function that says that all the values in the domain must be used. So you need an onto function, because when you reverse it, like an onto function means that all the values in the codomain are used. So when the codomain becomes the domain, that makes sure to give you a relation where all the values in the domain are used. Okay? So this example, let's say A is set 1, 2, 3, and the function defined on A given by these values, find the inverse. Okay, so this basically inverts the inputs and the outputs. So the inverse of 2 is 1, the inverse of 3 is 2, and the inverse of 1 is 3. Okay? So let's look at this example. So function f is from set ABC to set 1, 2, 3. so that A goes to 2, B goes to 3, C goes to 1. Is F invertible? Okay. So first let's look at our domain is A, B, C, and our codomain are numbers 1, 2, 3. Okay. I want to see if this function is a bijection. So A goes to 2, B goes to 3, C goes to 1. Right? So this is a bijection. Because it's 1 to 1 and onto, that means that it's going to be invertible. Okay, so if it's a bijection, it's invertible, and then I can write the inverse by reversing the input and output. Okay, so the inverse function is going to be a function from the set 1, 2, 3 into the set ABC with all the rules reversed. So -1, f of -1 at 1, that's going to go to C. Inverse of f of 2, that goes to A, and inverse of f of 3, that goes to B. And so here's a couple of examples of finding inverses with the functions given in algebraic form. So the g goes from the real numbers to the real numbers and is defined as x cubed. Okay, so the x cubed function is a bijection. And if I kind of think of what the x cubed function looks like on the real numbers, it's like this. Okay, so you can see that it's 1 to 1 to 1 to 1. So it's an injection. It's also onto because it uses all the real numbers as its images. Okay, so the range equals the codomain. So this is invertible. Okay. To find the inverse, the procedure is to say y equals x cubed. Then you switch the x and y values. You're switching the domain and codomain. And then you solve for y. So you're going to get y equals cube root of x. So this is my inverse. Like this. Cool. This should be familiar from algebra classes. Alright, let's look at function f defined from the real numbers to the real numbers as f of x equals x squared. So again, let's do a little sketch of this to see if it is invertible. Alright, so if I sketch the x squared function on the real numbers, I'm going to get this function right here. So notice this is not 1 to 1. It's also not onto. So this is not a bijection. Which means it's not invertible. Right. So the way we know to get around this, it's like, but I need to invert x squared. I know the inverse of x squared is square root of x. It's really useful to be able to do that inverse. Is that you need to redefine your domain and codomain. Okay, so if you restrict your domain and codomain, then you can make x squared invertible. Okay, so for example, if you define a function g that goes from positive reals, including 0, let's say that included zeros, to positive reals, so include 0 also in there, okay. Then the function that I'm looking at here, g, is going to be this part. Okay, so it's just going to be the positive part of the f function. Then this is invertible. Okay, because it is 1 to 1 over that domain, and it is onto over that codomain. And to find the inverse there, you're going to say y equals x squared, switch the x and the y, and solve for y, and you get the positive square root of x. Okay? Alright, we could have redefined this function differently. We could have said let's have the negative reals, including 0, going to the positive reals, including 0. All right, so the domain is the negative reals, the codomain is the positive values. Okay, and then you have, this means this portion right here for the negative x values. Right, and this is also invertible. So you can say y equals x squared, switch x equals y squared. Now when you take the square root, you have to take the negative square root of x. Right? When you take the square root, it's either positive or negative. You take the negative square root of x in order to get the inverse. Right? So even for something that's not invertible, if you restrict the domain and the codomain, you can break it up into sections that are invertible, and then you can work with them. Alright, so this is the end of this chapter on functions, kind of looking at them from what you know from algebra, but also kind of redefining them a little bit in terms of the discrete math stuff that we've been learning.